All right, Mr. Troll is back in his dining room with his shirt and tie on, pretending like he has a real job again. Here to introduce you to some abstract ideas here, limits and the derivative. So I was looking at this lesson in Canvas, and it's kind of a funny one. It's got some really good stuff about limits, some stuff that we've learned already that would probably be good for you to review about limits because a lot of you guys were scared of them and didn't really understand them very well, but you still made it through. Good stuff, good stuff, good stuff. There's some good examples here about how to analyze limits when the limits don't exist. Some really good practice problems to do to analyze different parts of a function with respect to limits at different x values. Really good stuff. You should do it. I'm getting excited. I'm like, okay, this will be good preparation for calculus. Then we get down here, and there's just this little blip about something called a difference quotient. And the bummer about this is all the quiz is on. I looked at the quiz and there's 5 questions and it's all based on this section here, this little blip, and then these 3 example problems that you can work through, and that's all the quiz is on. Unfortunately, on top of that, your textbook doesn't really have any questions in it, any practice problems that are anything like this one or this one. It has a few like this one, but there's only one problem like that on the quiz. So I decided that rather than do a video on this and all this information, do a series of videos on all this information, that would be a lot of time spent on stuff that you're not even going to be quizzed on. And I know that you guys would much rather me help you do better on the quiz. But I'm not only going to show you example problems from what's on the quiz. I am going to give you this video will be a little bit of a conceptual video trying to do a better job than this little blip of explaining what is this difference quotient thing, why is it also called the derivative, why is it so important, and why is this right here the formula for that. Okay. Like I said before, I'm not going to give you a list of problems from here, but I am going to give you a few problems back on the course page. You know how I usually put this little page link between the chain icon and the rocket ship icon. There's this page icon that I usually put practice problems and YouTube link. In here, I haven't published this one yet, that's why it's not green. In here, I'm going to put a few practice problems for you for this quiz, and I'll put the answers there as well. So that you can get some practice if you want before the quiz. Anyway, let's go to GeoGebra, where I am going to hopefully introduce this concept of derivatives successfully and implant it into your brains. Okay, so what is a derivative? Why is it important? And why is that the formula for it? Well, a better question to start with would be, given a function, here's this blue function. You can ignore all this junk over here for now. We'll get to that in a second. Don't let that scare you. Here we just have a function. Here's the equation for it. 0.2x to the third minus x squared plus 2. It's a cubic, right? A polynomial to the third degree. It has 2 turning points, right? Because of the leading exponent minus 1, that's how many turning points it'll have, and then that's also how many zeros it could possibly have. So this has 3 zeros. You know, the end behaviors are opposite, goes to infinity in one direction, negative infinity in the other direction. This is our friend, a cubic function here. Now let's suppose we wanted to know the slope of this function. Now normally when you're asked to find slope, it's not of a function like this, it's of a line. Right? You know how to find the slope of a line. The rise over the run, subtract the y values, subtract the x values, put that as a fraction, and there's your slope. Or you could find the tangent of the angle, right? A rise over the run, opposite over adjacent. Ways that you can find slope of a line you guys are good at. But how would you find the slope of a curve like this? It appears as though the slope is constantly changing, right? It depends on where you are on the curve, and you'd be exactly right. So if I was over here on the curve, it appears like my slope would be positive because I'm moving up to the right. If I was in this zone of my curve, my slope would be negative because we're moving down to the right. And if I was somewhere between there and there, maybe at this maximum point right here, my slope would be 0 there for just an instant. I would have a 0 slope as I move along the curve. That's correct, kind of, although we don't call it a slope. Okay, when you have a curved function like this that's not a straight line, it doesn't really have a slope, but it does have a derivative. Okay, so a slope is for a line, a derivative is for a function. Okay, so you can think of the derivative as kind of like the slope of a function, even though I hesitate to say that because I would be breaking the rules. Functions don't really have slopes except for lines. They have derivatives, okay? So the derivative is, you're looking at the slope of a function, really, but we can't say that. Anyway, so how do we define this? Well, let's just put a point on our function here, point f. Okay, so point f, I can slide around my function, and let's suppose I want to know, well, what is the derivative or slope of my function at point f? Well, remember, curves don't have slopes, but lines do. So I can draw a line through f where the slope of that line is the derivative of my function. Okay, so just like we said over here, it looks like our function is sloping positively, and the slope of my line is positive. Over here, it looks like my function has a negative slope, and my line is sloping negatively. And then up here, I've got that zero slope. Okay, so the slope of this line, this is called the tangent line. If you're observant, you saw that right here. This is the line that is tangent to the slope. What does tangent mean? Well, when you're not talking about the ratio of a right triangle, you're talking about a line that touches something at only one point. In geometry, we talked about tangent lines when we had a circle and then a line that touches that circle at just one point. That's called a tangent line. So this is the line that touches our function only at the point f. Okay? Now, can we find the slope of this line? Because if we could, that would be the derivative of the function, or the slope of the function at that point. How do you find the slope of a line again? You either need 2 points on that line to get the rise and run, or you need an angle and then you use some SOHCAHTOA skills to get the slope. Neither of those are available to us right here, right now. In order to find another point on this line, I would first have to know where the line is, right? And I don't know where the line is. In order to find the angle, again, I would have to know where the line is. So supposing we don't know the slope of this line, or don't know the line in the first place, how do we figure it out? And that is where the limit comes in. Okay, so let's, I'm going to hide that line, and we're going to move, I'm going to hide that line, and I'm going to move point F down here. Okay. Okay, now we're going to start talking about this craziness over here. So brace yourself. I want to know the slope of the line right here at point F. Let's take a peek at it, right there. I want to know the slope of that line. Okay. How do I figure that out? Well, I can't find the slope of that line, like I said, because I only have 1 point on that line. But I can find the slope of this darker red dotted line right here. That's called the secant line. Okay. The nice thing about the secant line is there's 2 points on there, that it touches my curve in 2 points, and because I know those 2 points, I can get the slope. Okay, so point F has an x coordinate, and that here is called x0, and it has a y coordinate, which is f of x0, right? If f is our function here, f of x0 will give us this y coordinate of f. So I know the x and the y coordinate of f. Okay. And then I find some other point further down on the function. Now, from my x-coordinate, suppose I travel along the x-axis by some amount h. Okay, and at that new distance, which would be x naught plus h, right? Here's x naught plus h. We'd be at x naught plus h. Now I take that x-coordinate, I plug that into my function, and I get this other point here. So I have 2 points on my function. Okay. I can draw a line that connects those 2 points. This is called the secant line. And I can get the slope of this line. Okay, remember the good old equation for slope is rise over run. Okay, so we subtract the y values to get rise, and we subtract the x values to get run. Okay, so let's subtract the y values. Well, the y value of this point is f of x naught plus h. And the y value of this point is f of x naught. So I would subtract f of x naught plus h minus f of x naught. That would give me the rise between those 2 points, right? Now let's do the run. Well, I could subtract x naught plus h minus x naught. We'd get h, right? Or you could just see, obviously, that the run between these 2 points is h. Okay, so the rise is subtracting f of x naught plus h minus f of x naught. And the run is h. And if we put the rise over the run, we get this formula, right? Where did I put it? Thought I put it on here. There it is. This formula right here, which is the same formula that we just looked at in our module right there. Okay. F of x plus h minus f of x, there's the rise over the run. So really this formula is just rise over run. We're finding the slope of a secant line. Okay. Now you might say, hold on, Mr. Troll. Yeah, we can find the slope of that secant line. That's all well and good, but weren't we supposed to find the slope of this tangent line? Yes. And that is where this limit part comes in. Okay. So notice how it says limit as h approaches 0 of the rise over the run. Okay. Now what's h again? H is the run. H is the distance in the x direction from one point to the other. Now, over here I have a slider for h, so I can actually make h approach 0. We can watch what happens. As h approaches 0, those 2 points get closer to each other, right? So my secant line is changing. What's it changing into? It is changing into, oh, it disappeared. What was it changing into? You can see it if I show the tangent line. It's changing into that tangent line. Okay, so I calculate the slope of my secant line, but I do that and I let h approach 0, and that secant line becomes my tangent line once h hits 0. Okay. Now you might say, oh well, what's the whole point of doing the secant line in the first place if we're just going to make h be 0? Well, then look at your rise over run equation, guys. What happens if you make h 0 here? You get a 0 denominator, and dividing by 0, you get an undefined answer. That's why we have to use this limit notation. Okay. Not only that, but you'd also get a 0 numerator, right? Because if h was 0, you'd have f of x minus f of x. That would be 0. You'd have 0 over 0, which is also undefined, and even a harder concept to wrap our heads around. Okay, so that's why we need to take the limit of this function or this expression as h approaches 0. Guys, I hope that made sense. That's basic calculus here. You're no longer a pre-calculus student, you're a calculus student. Okay, I know you haven't technically graduated from pre-calc yet, but this is basic calculus. So if you are even able to understand a solid percentage of this, then you'll be fine for next year. Okay, so in the next video I will do some concrete examples of finding the slope of this tangent line, finding the derivative on a function at a given point. We'll do that for 3 different functions. I don't know if I want to do 3 different videos or not. 2 or 3 videos are going to come after this one, and we'll do some of those examples. You got those practice problems in the module there, and then you got the quiz, and then we'll move on to 9.02. Okay, that's it for this video, guys. I will see you in the next one. Bye.